Hello, everyone. A very good morning to those who are joining us from Singapore and Asia, and good afternoon or good evening to all of you joining us from other parts of the world. Thank you for being here with us for today's online event on Banking on Quantum, the value of quantum computing in finance, presented by SGInnovate and partnered with the High Commission of Canada in Singapore. My name is Jin from SGInnovate, and as a Singapore government-backed investor, we have been building up and driving deep tech innovations in AI, healthcare, quantum tech, and autonomous technologies across various industries. At SGInnovate, much of our work is to connect Singapore with the global deep tech ecosystem to learn how we can better harness technology. Today, we have our panel of experts from Singapore and Canada to discuss why and how companies in finance should start thinking about their quantum strategies and the importance of the role of all stakeholders in supporting an industry's quantum readiness. We encourage you to engage with our speakers during the session by submitting your questions in the Q&A box located on the lower panel of your screen. Without further ado, I would like to invite our moderator for this discussion, Professor Paul Griffin, to start us off. Paul, please.
Hello, thank you, Jin. Thanks for inviting me. Hello to everybody. Yes, I'm Paul Griffin from the Singapore Management University, and we have four great panelists today who can give us some very broad and deep explanations of quantum computing, and also investigate how this can be used in finance. So I'm going to let them introduce themselves. But first of all, maybe Rafael Janik, if you could give a brief introduction to yourself.
Thank you, Paul. So as Paul mentioned, I'm Rafael Janik. I work at the Xanadu. And at Xanadu, we're really looking to build quantum computers that are useful and available to people everywhere. Part of this means that we have built a photonic quantum computer that is available through the cloud, but we're also looking at other quantum technologies to really enable the adoption of quantum computers. My background academically is in physics, but I would call myself a rehabilitated academic. I spent the last 10 years working in various companies, large and small, really pushing on machine learning, specifically computer vision systems for medical industrial applications. And then a year and a half ago, joined Xanadu to really focus on bringing its deep tech, its quantum computers, and make them available to people.
Great, thanks. Yeah. Next up, Andrew Fersman. Can you give a bit about yourself?
Yeah, hello. Thanks so much for having me. I am the CEO of a company called 1Qubit. We're really thinking about applications for quantum computing. Prior to that was co-founder of Satellogic, large number of small satellites in low Earth orbit. And my background is academically in economics, philosophy, political science, and finance.
Great, thanks. So a good broad set. So next up, Phil Kay. Can you introduce yourself?
Yeah, for sure. Thanks, Paul. I'm Phil. I work with the National Research Council of Canada, which is a Canadian government agency, the largest federal R&D agency in Canada. My academic background stretches back to the early 2000s. I was the first PhD student to graduate from Canada's Institute for Quantum Computing based in Waterloo. I then went and worked at for the federal government for Canada's cryptologic agency, the Communications Security Establishment, for almost 15 years. And quantum technologies was a theme that pervaded my entire career at CSE. I then went and worked at a company called D-Wave, a Canadian quantum computing company based in Vancouver, for about a year and a half. And this past spring landed at NRC. So very happy to be at NRC and happy to be here.
Great, thanks very much. And last but not least, Jane Thompson, can you introduce yourself?
Hi, my name is Jane. I work for a Singapore-based quantum tech startup called Horizon Quantum Computing, which does quantum software. My background is actually quantum information theory. Until very recently, I worked a lot in quantum algorithms and worked in Singapore in particular at the Center for Quantum Technologies. So I wouldn't say I was rehabilitated academic yet, but maybe getting there.
Great, thanks. So I think everyone on the call obviously has heard about quantum computing. That's why you're here. I think it's probably good to start off with you've probably heard all the hype and all the advantages and supremacy, etc. So let's kind of start off with getting a kind of a reality check. So I'm going to invite Phil, first of all, to give us his view on what is the current state of quantum computing, really, and then we'll open up to other panelists to add on into that.
Sure, absolutely. So whenever I start a conversation like this about quantum computing, one of the first things I like to do is to explicitly scope what we're talking about. And so what I want to do is just quickly review the distinction between computational annealing and quantum computing. Very different things. Sometimes they both go by the name of quantum computing, depending on who you're talking to, but qualitatively different approaches to computing. So computational annealing is D-Wave's technology, and it's a very special purpose computing approach to computing that is specifically, it's a special purpose type of computer that's specifically tailored to solving optimization problems, specifically quadratic optimization problems. What D-Wave does is tries to use quantum effects. It tries to use qubits to do annealing better and faster. One of the challenges for computational annealing, though, is that there isn't the same kind of theoretical foundation underlying it, and there isn't a clear or proven path from current annealing technology to something that is scalable, fault tolerant, and provides quantum advantage. There is some evidence that perhaps quantum mechanics is going to help with computational annealing, but again, that is still the jury is still out on that. Quantum computing, what I'll call quantum computing, on the other hand, what many would call gate model quantum computing, is an entirely different animal. In quantum computing, you have a very clear and proven path to scalable, fully scalable, fault-tolerant quantum computing. A very challenging path, and as we'll see, the technology path to be followed is very, very challenging. But there is nonetheless a clear path forward. There's proven results that there's nothing fundamental that's going to stop us from one day building fully scalable quantum computers that we know for certain problems will vastly outperform anything that classical computers can do. So where are we now with building quantum computers? Of course, as I said, it's very, very challenging. The types of qubits, the types of quantum bits you need, the level of control you need over the quantum bits in a quantum computer is significantly more challenging than what is needed for a computational annealing quantum device. And so where a D-Wave machine has 5,000 quantum bits, the largest gate model quantum computer at this point, I believe, is IBM's with about 65 quantum bits. And that is a slow and steady march. IBM has actually promised recently 1,000 qubits by 2023, which I think is a hugely ambitious goal. But if they think they can achieve that, then that's going to be a very significant result. And I'll tell you why 1,000 is kind of an important number in a minute. Meanwhile, there's Honeywell, which is also doing quantum computing, although their physical qubits are based on a different technology, where IBM's using superconducting technology to build their qubits. Honeywell's using trapped ions. Their quantum computer is 10 quantum bits currently, I believe. And then there's another approach to implementing your qubits. You can use photonic qubits based on states of light. And Xanadu does this, and I believe Xanadu's quantum computer is about 12 quantum bits. One thing I should briefly point out, though, is that counting qubits isn't the full story. If you remember back in the 90s, when everyone was looking at clock speed as the way to measure how fast your desktop computer was, and then they realized that there are other things that could measure the power of a computer. How high quality your qubit is, how much noise your qubit has, how long your qubit can last. For example, how many gates can you put your qubit through before it loses its properties? These are important characteristics too. And so there is a measure called quantum volume that IBM designed to try to account for this. And to give you a bit of an idea, where, as I mentioned, IBM's quantum computer is 65 qubits and Honeywell's quantum computer is only 10 qubits. Honeywell brags, or brags, boasts a quantum volume of 64, and IBM, actually I think Honeywell's up to 128 now quantum volume, and IBM's around 64. So 6 times the number of qubits, but only double the quantum volume. So clear as Xanadu, I'm not sure what the quantum volume is. Rafael can probably talk to that later. But all that to say, the path to full scalability is very difficult. One of the key milestones we need to get there is what's called a fault tolerant qubit. These qubits that I'm talking about when I'm saying 10 qubits, 65 qubits, these are physical qubits. So a physical trapped ion or a physical superconducting loop to implement a quantum bit. Because they're physical devices, they're prone to errors, they're prone to imperfections, and so we call these noisy qubits, and they're qubits that are prone to errors. If you want to be able to, the problem with noise is that it compounds and it propagates, and so the bigger you make your computer, if you're taking a noisy qubit and then you have 10 noisy qubits and then you have 100 noisy qubits, eventually the errors that are being generated in those qubits are going to overwhelm the computation and you won't be able to do anything. So in order to fully scale a quantum computer, you need to do error correction, and you need to implement what's called a fault tolerant quantum bit. And that's basically a quantum bit that is error corrected to the point that you can do operations on it as long as you want. And you can scale as many as you want. There's a lot of overhead required, though, to turn a physical qubit into a fault tolerant qubit, and it's about the order of 1,000, depending on the approach you use. It can be about 1,000 times overhead, which means you need 1,000 physical qubits to implement one logical qubit. So that gives you an idea of these significant challenges to build scalable, error-free quantum computers. What we have in the meantime are referred to as NISQ, NISQ, near-term intermediate scale quantum computers. And these are the quantum computers that have sort of fewer than 1,000 of these physical imperfect qubits. And that's where we are today. One of the main challenges on the application side is that we're trying to figure out what can we do with these NISQ quantum computers? Are there any applications that for which a noisy intermediate scale quantum computer with maybe a couple of hundred physical noisy qubits can outperform what we can do classically? And there's some evidence, there's some hope that there are going to be some applications. Some of the leading candidates for promising applications of near-term intermediate scale quantum computers are in quantum chemistry simulations. Being able to simulate physical systems, chemical systems at the quantum level, which is important for a variety of materials design or other applications for simulating electron transport, all kinds of things in things that I don't understand in biology and protein folding, all that kind of stuff. Finance, I'm not sure. I think there are other speakers today are going to speak more to the potential for applying near-term intermediate scale quantum computers to finance. I'll just say a couple of brief words about some of the software stacks, the application space, and some of the hype that's now being generated. We're seeing an explosion of commercialization. All the companies who are putting quantum computers on the cloud now have their own software stacks. They have their own programming languages. So IBM's got Qiskit, Xanadu's got PennyLane, Microsoft has its Q# language. There's a company called Zapata that's building whole workflows that are sort of hardware agnostic. There's all kinds of amazing, cool stuff going on. But at the same time, that's also generating a lot of hype and to a large extent, I think, a set of inflated expectations around that people are seeing all of this advanced sort of technology work being done on the software side, and that sort of leads them to believe that, oh, well, the underlying algorithms must already be there. And of course, a lot of what we see in the media sometimes fuels those expectations. So I think, especially in applications like finance and stuff, there does need to be a bit of a reality check and where really are we and what is proven and known about what we're going to be able to achieve and what is speculation and not strictly blind speculation, but what is speculative, I'll say, and early stage work that's exploring the space.
Right, sorry, Phil. Yeah. Well, actually, why are we on this subject of software? Just wondering whether I can switch to Jane now to say a bit more on the software. So I think you've given us a great overview of the current situation, the hardware and things. So I think maybe Jane, if you can say a bit more as you're working for Horizon, which is kind of software-based company, if you want to sort of expand a bit more on the software side. So sorry to cut you off there, Phil, but Jane, yeah.
Phil did a really good job. So it just made my job a lot easier. But maybe I can talk in the context of the software, as that's what I would know a little bit more about, as opposed to the devices and the current state of the art.
Yeah.
So, and maybe in the context of finance as well, to put that into the discussion. So we should be really excited about the potential for integrating finance tools into quantum software stack. This is actually very promising. And there is good academic reasons for being interested in this and believing in its potential. So for instance, this comes from basic capabilities of quantum computers, maybe not so much the hype, but what we know that they're really good at doing. And in particular, we know quantum computers are very good at simulation and prediction tasks. So they have really strong algorithms in quantum search and quantum walk. So these power things like faster hitting times to simulate from the long-term behavior of a system more efficiently quantum mechanically, quantum Monte Carlo methods for estimating a parameter to a certain level of precision with quadratically fewer samples quantum mechanically. So these are really solid. And a lot of the quantum finance applications are being built on these. Things like conditional value at risk, portfolio performance, estimation, optimization. They are actually built on the solid tools of the simulation and the walks. So hopefully the software will pull in these elements. I believe it is already pulling in these elements because this gives it a very strong foundation. Also matrix algebra, really promising techniques in matrix algebra, quantum algorithms for solving linear equations, singular value decomposition, quantum principal component analysis, eigenvalue and eigenvector resolution. So there you get your quantum machine learning advantages, a lot of them. Your advantages in things like classification, prediction, even regression, curve fitting, inference of relationships from data sets. All of this will actually come through from this tool chain. And again, I can see a lot of really good progress in the quantum software companies on this front as well. And in addition to that, you obviously have a role to play in terms of optimization on quantum computers for solving financial problems. So this is like, this would take me an hour to talk about all by itself. But I mean, you're looking at variational quantum algorithms, quantum approximate optimization algorithms, and maybe even things like adaptive quantum search, which are coming through and allowing you to do a lot of optimization as long as you can design a good cost function, which is a good proxy for what you're trying to minimize and also is efficiently evaluable on the quantum computer. So this software algorithm suite is very strong. The applications and the use cases is actually in the software domain a really big point of progress at this moment in time. And of course, as Phil said, the hardware is also like matching our expectations against the hardware is obviously going to be something which we should be very interested in doing, as otherwise we'll just overhype. And I definitely agree with that. So you asked me for an example in the question you sent me. So if you're still interested in the example.
Yeah, I think that'd be an example. And how easy is it for someone to actually start programming these quantum computers? If you've got a background, say, in just Python machine learning, can you just sit down and start banging out quantum?
So I'd say if you have a background in Python machine learning, like some other people here, you're very smart. And you should actually really have no problems because you're good at handling data structures and you're good at handling abstract objects. And really, quantum computers are just really sophisticated tools for harnessing these particular capabilities. So I suppose that this question might be tailored almost to me because I'm coming from Horizon, and what we actually do is we allow you to program in classical conventional computer code, and then we automatically accelerate your code by just sort of automatically inferring or recognizing where you could have used the quantum algorithm to do it faster. So, and this is a very good question for Horizon in particular, but obviously I actually think that you're going to be really good, in a really good position to use the tools of most of the quantum software companies because you have the good analytical knowledge if you're able to do this. But I did prepare you an example, so I'm glad you want it, which is the Gaussian process regression. And why would you be interested in using quantum software tools in this context. I'm told that this is actually, to start off with, this is a technique for actually inferring functional relationships on training data sets. So you give me a training data set and I infer the functional relationship between the points in it. And in particular, I want to do this because I want to take another point which is not in my data set, which I am curious about, and I want to make a prediction about how it's going to perform. So you, in particular, see applications in finance for this apparently in the context of future prices of commodities. And to give you an idea about why you should be interested in harnessing quantum computers to do this, as a case study, if I was to take 1,000 data points and train my function off this, I'll get a certain level of accuracy, and this will be good. But if I do this on a classical computer, and then I want to get a higher accuracy by invoking 1,000,000 data points instead in my training set, then I'm going to take more than 1 billion times slower to run the computation in a classical computer. There might be some special cases where I might be able to get it down to 2,000 times slower, but the general paradigm is I'll be 1 billion times slower to train up 1,000,000 data points than I am to train up 1,000 data points. And this is just due to scaling in classical computational routines. It's a scaling issue in which you add a new data point to the training set and your classical algorithm gets slower in a kind of non-linear kind of way. Quantum mechanically, you don't see the slowdown. Quantum mechanically, you can train up 1,000 data points and then you can want to increase your accuracy and train up 1,000,000 data points. You'll only slow down by a factor of 4. So what you're actually looking at is really strong advantages in terms of scaling for this kind of basic matrix linear algebra operations on a quantum computer, which is what's actually the backbone of this routine. So if you have really good data analytics skills, you should be really quite excited about what you can do by just upgrading your routines by running certain key bottleneck steps on the quantum computer. And I'm absolutely convinced that you are in a good position to try this. Of course, I should caveat what I'm saying, which is that Phil is absolutely right. I won't run this on today's NISQ quantum computers. Obviously, the hardware has an error rate and a number of qubits, which isn't compatible with running such an ambitious 1,000,000-point training program for fitting a function. But there is a very good promise that the hardware is actually leveling up at a very incredible rate. I'm sure Xanadu is going to tell you about their progress. I've been reading quite closely and I'm quite excited to hear about this. And the software is very much leveling up to anticipate that the quantum computing will become a much bigger player in many different industries. And that's something which everybody should be able to access. So I do believe that you have every opportunity, given the impressive collection of quantum software expertise out there, to actually give it a go if you're good at data analytics and data structures.
Great, okay, thanks, that's great. So we've got an idea about the hardware, heard about software. I'm going to hand it over now to Andrew and ask about the wider financial applications. You say you've got a background in economics and finance. So how is quantum computing being applied now, will be applied? Is it just scaling speed up, or is there something kind of maybe, I shouldn't say maybe more exciting, but even more exciting that quantum computing can do in the area of finance? Over to you, Andrew.
Thanks. Well, I would answer your first and easiest question first by saying that what are quantum computers doing in finance now? And the answer is receiving funding from financial institutions. But in terms of providing actual value, it's really like saying, what do people do with the first transistor? And on the one hand, the answer is almost nothing. But on the other hand, you can see this as an incredibly important moment in the history of computation. And we're a little bit past there right now, but we're still sort of at that, in 1 to tens of qubits. And so there's a lot of things that we would like to be able to do, but the hardware is just not quite there yet. And so probably another interesting question is, well, how will we use quantum computers in the future in order to solve problems? And, I don't have a crystal ball, and there is a lot of work to be done there. But what we do have is the history of financial and computational finance. And so one of the things that I find really interesting is looking back to how computers were initially utilized in sort of big ways within, say, financial markets. And so when I think back to the ideas of, if anyone's taken any basic finance in school, you might have learned about the Black-Scholes algorithm for pricing financial options or financial instruments in the future. And what's interesting is that what was actually utilized in order to succeed there was somebody kind of recognized that the trajectory of the stock market looks a little bit like the trajectory of, say, a rocket. And that the correction of that trajectory as it's sort of going up and down, utilizing techniques that were designed in order to simulate rocket trajectories, there was an understanding that there was an applicability. And so, if you traditionally studied like Ito's lemma and things like this, probably you were a physicist doing rocket engineering, but eventually people realized those same tools are extremely helpful for us in doing this analysis and simulation within finance. And so I think that we're probably going to follow a pretty similar path where what you're going to see is quantum computers are initially going to be utilized for material simulation and simulation of the quantum world, meaning essentially we want to know things about the way quantum information interacts, and quantum information naturally interacts within the physical world. And so we're going to build very important tools for doing things like understanding how chemistry emerges from physics. And I suspect that what's going to end up happening is that some of the tools that make it so that quantum computers are applicable within the world of physical world simulation are going to become repurposed and being applied to financial applications. And so for me, one of the ways that I think about the question of how close are we to utilizing quantum computers within finance, and how do we know when it's getting closer? I think one of the answers will be, we will probably start seeing quantum computers applied to the discovery of new materials, specifically things like catalysis, understanding, what matter can you put into a physical chemical reaction in order to either speed up or slow down that process. These things feel a little bit more within the wheelhouse of quantum computers. But once we start to succeed with those, very direct explorations of quantum information using these quantum information devices, that will really open the floodgates to be able to start thinking about some of these slightly less direct applications of quantum computing. And I think many of the applications that were discussed, just previous, are exactly the sorts of things that we're looking for. But it is important to note that when we were talking about the number of qubits, there were two things that I think were very important. One was, if you have something like 1,000 qubits of a certain type of qubit, that's actually kind of like having one error-corrected qubit. And so whenever we talk about how many qubits people will need to do these sort of financial applications, we're probably talking about not these noisy intermediate scale quantum devices, but instead sort of full-scale fault-tolerant error-corrected devices. And on top of that, you probably, for these kinds of financial applications, need on the order of thousands, if not tens of thousands or even millions of qubits. And so we are very far away, I think, from utilizing circuit model quantum computers directly to solve financial problems. The other thing that's really interesting to think about here is the fact that when we think about competing against regular computers, because that's probably the competition, it's not as though it's quantum computers or pen and paper. We now have this much more difficult task of competing against the moving target of classical devices. It's also worth noting that quantum computers are inherently very slow today compared to the clock speeds of these classical machines. And so it's not only a challenge to find out things that you can do with a quantum computer, it's important to find things that you should do with a quantum computer, because there's no other good way to be able to solve that problem. And so that actually makes this exploration very challenging, because essentially you have to go to a finance organization and say, what's a really critical thing that you wish that you could do, or else your company is going to be in dire jeopardy, that's impossible for you to do any other way today. And of course, there are no such problems, because if we had those sorts of problems that were stopping us from having a company, we wouldn't have a company. And so we're really sort of trying to get people to stretch and think about, if you had this new type of device, what sorts of things would be really valuable to your company that you're not able to do today? And I think that's going to come from not so much, physicists in a lab thinking about finance, but financial practitioners having access to some of these devices and getting much more deeply engaged. And so I think the best argument for having people in finance start thinking about quantum computers today is not the expectation that they're going to be able to make more money in the markets today, but instead because there's a lot of thinking that needs to happen on that idea of how can we harness these special capabilities of these quantum devices in ways that provide real value for people in the finance industry. And frankly, that's still an open question.
Okay, so thank you very much. I think we'll take that open question to Raphael to give him his comments on what's happening in your space. And also I'd like to bring in the idea of the quantum internet, of actually not just running quantum computers individually, what's happening in the, maybe you can talk a bit about the photonic side and connecting up computers, and maybe even, where we're going to end up when we do have a quantum internet, and whether that's 10 years, 20 years, 50 years.
Yeah, absolutely. Maybe first just to comment on what's already been mentioned. One thing that's kind of been implicitly mentioned is that a quantum computer is wildly different than the classical computer, and not only in the way that it operates, but actually in the things that it's good at. It's something completely different and unique, which means that the problems it will tackle and be able to solve are not problems necessarily that we're thinking about today. So a lot of the algorithms that do exist that are being applied to financial problems might have very familiar sounding names, but actually come with a whole bunch of caveats that most people in finance don't normally think of. So, quantum Monte Carlo is a perfect example, but through our interactions here with different financial institutions, a lot of the things that they would naturally love to do with their Monte Carlo runs, you can't do with a quantum Monte Carlo. So it might give you this quadratic speed up, but there's other limitations. So that's the negative side, is that often, just knowing that this exists and has a speed up is not the whole story. It's also like the details in the implementation. So even with a fault tolerant universal quantum computer, the clock speed and how many of these qubits you need actually to build a single fault tolerant qubit means that any of that speed up might actually disappear. But this is kind of the negative. On the positive, there's whole classes of problems we don't think of in finance anymore because they're not tractable by classical computers. So things that people have absolutely never thought to try to solve, or have forgotten that were problems and worked around them, that with the advent for fault-tolerant universal quantum computing could potentially become tractable again. And there's almost like a call to action for people in finance to start learning about quantum today, in order to start unlocking what those applications are. On the really negative side, I think probably the thing that a lot of people would have heard, which is maybe the stick that us quantum companies use to get people motivated to start investing in quantum, is this idea that one very well-known algorithm is one that can break public key encryption. So Shor's algorithm has been demonstrated to be able to tackle elliptical curve encryption problems, which is what the majority of public key encryption schemes that we use to secure our data today is based on. So this is something that we're facing. There's ways around it, and one of those ways are kind of the beginnings of what we would call quantum networking, or eventually the quantum internet. So quantum key distribution is a technology where we can leverage similar principles that are used to build quantum computers to actually exchange information on a public channel in such a way that we can basically understand when it's being intercepted. And in this way, we can exchange keys that nobody will theoretically be able to break. And this is really the first form of quantum communication that's been around now probably for well over a decade. And there's been various efforts around the world to deploy these networks. And we're starting to see more and more financial institutions invest in proofs of concept of how to secure their communications with such technologies. And then if you keep on pushing that forward, this idea of a quantum internet, the ability to actually exchange information in its quantum state between two quantum computers emerges. But for that, the challenge to build those types of networks is actually probably more difficult than building a fault-tolerant universal quantum computer. So it's still a ways away. And the really challenging thing is that much with like the internet, many decades ago, we don't actually know what all the use cases are of a quantum internet. Today, we can think about a handful, whether it be networking quantum computers, quantum sensing networks, but it gets really challenging to actually think about what the broader applications will be.
Great, okay, thanks. Yeah, we've got some questions coming in just about on time as well. So I'll start off with probably two questions in one from Anil. Saying that, and I'm sure some of the panelists can answer this, what is a real use case being worked on now in banking, and what is the actual business point of view? So, I mean, yes, we're all interested in maybe it can do fast in the future, but right now, is there a real use case with a real business case behind that use case that's been worked on? Does anybody have an answer for that?
I mean, if nobody's going to jump in, I'll happily go ahead. So we have carried out a series of projects. It really depends on what the purpose is. The majority of the projects that we engage on, and I think most do, are focused around quantum readiness. So actually getting the knowledge within financial institutions so they can set direction. Usually I like to think of it as a de-risking future investment. So those ones are usually more further looking out and have been focused things on like quantum Monte Carlo for pricing of complex derivatives, or for looking at using Monte Carlo for economic models for regulators, or even meeting regulatory requirements. But those are things you're realistically not going to be running on hardware today, but it will give you a good understanding on what are the hardware specs that you would need to actually achieve this. On the other side, there are applications that maybe within the next 12 months could see quantum advantage. So things where you could actually start running on hardware and seeing performance that is better than what you could do classically. And these are usually focused on optimization, combinatorial optimization problems. So things like looking at portfolio rebalancing, or even things like attempting to detect arbitrage opportunities within certain markets. So, the applications are fairly broad, but I'd say they fall into one of two main categories right now for most of the work that we've seen. Either the quantum Monte Carlo modeling type of projects, or the combinatorial optimization type of work. There's a whole other aspect that people do get involved in, which is quantum machine learning. And at Xanadu, we love it. We have our quantum machine learning package Penny Lane, which works on any hardware with any backend that you're interested in. But quantum machine learning, it's incredibly difficult to prove when you actually have an advantage. Which portion of that hybrid network is doing the heavy lifting, whether it's the classical part or the quantum part. So I'd say we like to use quantum machine learning as a gateway drug to get people into the world of quantum, especially if they're coming from machine learning. But usually, if you're looking for, near-term ROI, real ROI, you'd probably be focusing on those other types of problems.
Right. Okay, thanks.
Can I jump in with just a comment on the quantum machine learning? I like that description of it as a gateway drug, but I guess I just want to point out that one risk I see with that is that because machine learning is so important to such a wide range of applications, and it is it's what everyone's thinking and talking about now. I worry sometimes when quantum computing gets hitched to the ML sort of bandwagon, because to me it sets up an expectation that if it is not met, because at least to my knowledge, it is not yet really known what the advantage of quantum computing will bring to machine learning or to AI. And if quantum computing fails to deliver on that promise, then people, that may have an unfortunate effect of undermining confidence in quantum computing for all sorts of other things that besides ML that it might succeed at.
Yeah, maybe just to add to what Phil said, one of the the reasons that quantum machine learning is so popular is because we don't have fault-tolerant universal quantum computers. So when we have these NISQ era devices, it's difficult to program them kind of with ahead of time with a given algorithm. It's a lot easier to treat them as a black box where you have a handful of knobs that you can actually turn to get the output that you want. So then the idea that you can train this black box looks very familiar to people who come from a quantum machine or from a machine learning side, where they're used to building a neural network where they're just going to use gradient descent in order to optimize it and get out the answer that they want. And in a very, very similar way, you can treat near-term devices where you just throw data at it and turn the knobs until you start getting the results that you want. But like Phil said, what the advantage is still a big field of research.
I guess you get quantum machine learning.
It's maybe worth
complex. Okay. Well, I mean, you get quantum machine learning, which has to do with the solving linear equations, style speed up, but then you usually have a question about how you're going to handle the QRAM and the data load in. Or you get quantum machine learning and the variational methods, but then unfortunately you get hit with the barren plateaus problem. And there's certainly a lot of debate as to where exactly it will be useful. Certainly in NISQ devices, it's very promising to actually use it as a way to actually begin to appreciate what might be handled on a quantum computer efficiently. But you should definitely have some circumspection about any conclusions that you draw.
Great. Okay, thanks. Yeah.
One thing that I think is really interesting in that space is that if we think about when we say machine learning, we almost always mean deep learning today. And of course, there are a number of other different types of artificial intelligence or machine learning methods which have been proposed over the years that have different requirements than, say, just the matrix multiplication that forms the workload from most of the work that we have right now. So an interesting question would be, are there other methods, including I'm particularly interested in sampling methods that could be used on quantum devices in order to animate some of the less favorable methods of machine learning, or let's say methods of machine learning that are out of favor because their strengths aren't matched with the capabilities of current hardware. And so one of the things that's really interesting, and I think which sits on top of something that was what Phil said to really kick this off, is when people talk about quantum computers, they mean a number of different things, including quantum annealers and universal circuit model quantum devices. But we might also be able to use application-specific devices that have been produced in order to take advantage of one very specific quantum function in order to animate, for example, a method of machine learning. And so I think that there is also other things other than sort of universal quantum computers, which may be helpful within expanding machine learning, because again, quantum computers are not just fast classical devices. They're sort of very different computing devices that have very different strengths and very different weaknesses. And if we can tailor our methods to match the strengths and weaknesses of some of those devices, that might be a little bit easier than trying to think about how we can try and outdo what classical computers do so well on the same problems, which is almost impossible.
Actually, this is really fascinating because I had a chat with David Wolpert about exactly this earlier this year. And he's the guy who invented all the no free lunch theorems in machine learning. And he said that he was there when they were first developing the machine learning paradigm. And Andrew Nung set an assignment for his students and realized that backpropagation could be accelerated on conventional GPU graphics cards. And then he said there was a watershed movement where machine learning all went to deep learning, well, not deep learning, but backpropagation. And right. He said that before this, there was actually a much more rich texture. And this was exactly his point. His point was, instead of trying to follow the classical paradigm, it's only a classical paradigm because there's a cheap, readily available chip already widely distributed. And it was only when they found this that it became the classical paradigm. And his point was actually, well, what happens if you mix it up? What happens if you accept some of the other paradigms as well?
Yeah, and that's exactly along the lines of some of the thinking that we've been doing, which is really to say that the success of deep learning kind of required this miracle where the method was built after the chips that could accelerate it already existed. And if we're going to rely on miracles in order to advance the state of the art, we might be waiting for quite some time. But if you can think about what would you need to achieve computationally in order to accelerate some of these out of favor methods, I think that's a very rich area of exploration and probably a conversation we should have together beyond this.
Yeah, it's a really interesting question.
Yeah, I mean, one of the things we're looking at, it's a project at SMU in the quantum machine learning, is how is quantum machine learning different from classical, different data patterns, different resilience to noise. How, you know, can it be used alongside classical to give another aspect, another kind of accuracy to the data, as you know, that adds on to what is classically there already. So there's a few kind of, trying to see what's different about quantum machine learning to classical machine learning. Okay, thanks. Just to kind of switch into a different mode, there's an interesting question here about, out of all the industries, do we think that finance will be the first to widely adopt quantum tech? If not, then which industries might do that? Especially interesting to hear from Phil from the Canadian government perspective. So that kind of broader quantum tech, which industry is going to jump on it first or most?
Sure, yeah. So the first part of the answer is that no, I don't think that finance will be the first applications where we'll actually see quantum advantage. And again, this is just my opinion. I think, you know, at NRC, there's a lot of interest in, at National Research Council, there's a lot of interest in the simulation applications. So simulating chemical reactions. Simulating chemical reactions is obviously very important when you're trying to increase yields for chemical reactions for producing things like fertilizers or other chemicals. So it's in a sense, it's a simulation problem. It's also sort of an optimization problem when you're trying to design new materials that are very hard and important optimization problems that have to be solved. And so some of the variational quantum algorithms that people are exploring now could have applications there. And there's actually a company, a Canadian company called OTI Lumionics that designs special materials for displays and other things, and they are looking at using quantum computers to help augment some of their optimization techniques. And then there's also more traditional optimization applications, you know, around logistics, you know, allocating resources most efficiently. And the nice thing about optimization problems, of course, is that they also lend themselves to being tackled by computational annealers, both classical and quantum. And so that can inspire and stimulate the development of the quantum technology. So the quantum technology that D-Wave has to develop for its computational annealers, superconducting qubits, you know, is also very relevant to building gate model quantum computers. And I see another question, and I just want to quickly add to it because it is sort of relevant to this. There was a question about using quantum computing to tackle large sets of data or tackle problems where you've got huge amounts of data, and that, at least to my knowledge, is a misconception. That's actually very challenging for a quantum computer, because for a quantum computer to be able to compute on a huge data set requires what's called a quantum memory, a quantum RAM. So not only do you have to be able to store a quantum state, a register of quantum qubits for a long time, but you have to be able to access those qubits, you know, on demand. And that is a very, very challenging technology problem that still has to be solved. So I don't see those kind of big data processing applications being one of the first applications of quantum computers. You know, eventually it may come, but not one of the first. I think optimization and simulation are the core ones.
Maybe just to add to...
Oh, sorry, please go ahead.
I was just going to say, maybe to add to what Phil was saying, I completely agree that, again, places where quantum simulation is going to be needed is really where we're going to see advantage first. But we're definitely seeing financial institutions invest quite heavily in the early days of quantum. And I think it's driven by really two factors. One, there's really a talent shortage in the space right now, and it's going to continue to exist for quite some time. So even if you believe that your application is going to show up in the next 5 or 10 years, you really need to start building that expertise internally now in order to be able to leverage it when it does show up. The other one is really driven by what I would say is probably the intellectual property environment in the United States. And the fact that financial institutions in the United States have started acting a lot more like tech companies in terms of building patent portfolios to go after their competitors and defend themselves. And quantum is currently seen as a bit of a green field for this. So there's a very aggressive, I would say, land grab that is happening in terms of trying to build out IP portfolios so you can operate when you do assume that there will be a quantum advantage by cross-licensing. And final follow-up on Phil's last point, which is big data is not well suited towards quantum computing. I love it. I think it's something we hear very often that people ask about that. I normally like to think about the problems that are best suited are problems that it takes a very small amount of data to describe, but have a very large space to explore for a possible solution. So if you can think that within, 10 or 15 numbers, you can describe your problem, but the possible number of solutions is in the trillions, that's the type of problem you want to be looking at for quantum computing.
It might also just be worth noting that in addition to the fact that I think I agree with the consensus here that material simulation might be one of the low-hanging fruits or one of the first things that people toss us into, it really kind of depends on your definition of first, because one of the most challenging algorithms to implement, Shor's algorithm, was conceived and written down long before there were actually quantum computers. And most people who are building computers or quantum computers now agree that Peter Shor's algorithm is completely, it's sane, it's sensible. If we had the kind of computers that we're all trying to build, then an algorithm that was written almost 20 years ago would be capable of running. And so when we think about finance from that perspective, it could be the case that the first industrially relevant application for quantum computers is something that's available significantly before the quantum computer that's able to run it. And that's probably still very important, because if we had the understanding that financial institutions would be able to radically reduce costs, say, by running a particular application, then there'd be significantly more demand for these machines. And so thinking about the software, even in the abstract, is very motivational and very helpful for being able to invigorate this industry.
Another aspect to build on what Andrew was saying is that because we haven't had machines to play around with, we haven't been able to develop, until very recently, we haven't been able to develop heuristic type of algorithms, right? We've only, when I was in grad school, Pete Shor's algorithm was discovered actually 25 years ago. And at that time, the only thing you could do was sit down with a pen and paper and draw out a quantum circuit and then prove some complexity bounds. Now we are actually able to sit down with 50-qubit quantum computers and try things out that we can't prove any results about and see what happens and see what the behavior is like. And that's, I think, a huge space of unexplored space that's going to be really exciting.
Yeah, it will be exciting. I think there's a second question coming up in all of this, though, which is data loading. Like if you have a big data set or you have something which is very complex, do you have an efficient way of loading that in and describing that? So you might have a very complex system, like a chemical system, but you might have an efficient way of representing and loading that database. You might have a very large matrix, which you wish to look at the expectation average of how it behaves or its trace, or maybe a partition function for a very large spin system, but you have an efficient load-in actually in terms of 1 and 2 qubit gate decomposition of that matrix. And in a similar way, the Gaussian process regression, you don't touch QRAM. You actually load it in the oracle and the matrix. So actually, this comes back to Raphael's first point, which is if you use these things very naively, and in the Monte Carlo sampling case, which is actually a good proven, theoretically strong result, you won't necessarily get your advantage. It's not a hammer to break all problems. It's something which you have to use relatively intelligently.
Okay, thanks. So we're getting towards the end of our hour. So I just want to ask the question of, general question of how does someone who's interested in quantum computing start? Where do they go to? What do they do? Do they have to become a quantum physicist, read quantum physics books before they start? Or, who would like to take up the question?
Well, I can start by recommending a good textbook, although it's 16 years old now. So I wrote one of the seminal textbooks on quantum algorithms, and we made a very concerted effort to write a book that would assume that you didn't know anything about quantum mechanics. And in fact, you know, one way or another, when you learn quantum computing, you are learning quantum mechanics. You're learning the concepts of entanglement and of superposition, but it is very possible to do that from a strictly linear algebra perspective. I guess I maybe want to, you know, while there are now toolkits and software stacks and things that now enable somebody, you know, just to learn a few lines of Python and apply quantum algorithms to understand and develop new quantum algorithms, you really need to, you know, the barrier is a fair bit higher. The mathematical tool that you need to understand these things is linear algebra. You need to have a strong basis in linear algebra, basis, and pun intended. And that's so if somebody really wants to understand what a quantum algorithm is and how it's working, how quantum interference you know, generates these unique capabilities, go back and brush up on your linear algebra, and then there's a number of textbooks now available, but that's, you know, I don't think you can, there's no shortcut to doing the hard work.
Thanks. Anybody, any other avenues? And I know that IBM have their IBM Q network with free quantum computers available. They have a development a sort of IDE interface to it, and you can sign up for free. They've got tutorials and stuff as well. So that's another kind of a practical avenue. Any other suggestions?
I would offer the gateway drug of quantum machine learning through Penny Lane. So Penny Lane is an open source package, Apache 2 licensed, community developed, that Xanadu kind of started off and still shepherds along the way, but full of great tutorials to get you started. Again, like Phil said, there's really no replacement for doing the hard work, learning the math and understanding the algorithms. But if you want to get a sense of what it is like to work with these devices, what it's like to actually run on them, really one of the easiest ways I found is through Penny Lane. And you can access the IBM machine, or if you feel like it, you know, go through something like AWS Bracket or Azure Quantum to access a range of devices, and yeah, start on your favorite things that you can do on near-term devices today.
Great, okay, thanks. So yeah, just the last couple of minutes now. So I just want to go around everyone finally and just ask, unfortunately we can't get to all the questions, but we just ask for the panelists what their final one thought for everyone to leave this with. What's the key thought to leave for everyone to leave with? And then maybe Raphael, as I can see your face on the screen at the moment.
I'm going to say it's cheap to get started today. It's only going to get more expensive as we move forward. It's limited with the number of people. The moment that quantum advantage lands, the demand's going to go up. So I'd say build within your institutions some initial expertise around quantum, not so you can start leveraging it today, but so you can plan accordingly for the next decade as the developments come along.
Okay, thanks. Jane, your final thought?
Yeah, I would say don't plan in the face of uncertainty as much as you can. Work out how you can get some advantage out of this if possible. And you're not going to see benefits today on this computers for a hard problem which you can't tackle in your classical. That's fair enough. It's really about planning for the future.
Yeah. Okay, thanks. Phil?
Sure. I'll just, I guess I'll give my sort of crotchety old man sort of warning. Don't put the cart before the horse. Don't skip the fundamentals. Don't just go and you know, learn Qiskit and then call yourself a quantum programmer. Do the hard work. Learn the fundamentals. That's the only way we're going to expand the field. It's new people making new contributions and new algorithms, and to do that, you have to do the hard work.
Great, thanks. And Andrew?
Yeah, I think maybe just the really important thing to understand is that quantum computers aren't magical computers. They're not computers that are better than classical computers. They're just something very different. And so the thing to think about is problems which are already being solved by classical computers will probably continue to be solved by classical computers. And so the real sweet spot, the opportunity that exists right now for everyone who's watching this, is recognizing if this is the strength of a quantum computer, and understanding what this is requires the hard work that Phil was just talking about. But once you have that ability to understand, I see how a crux of the thing that we would like to be able to do is empowered by the capabilities of that machine. That's the real sort of aha moment that's going to lead to these next breakthroughs. And so I think that it's very important not just to understand the quantum information theory component, but also really to deeply understand the areas that you would like to be applying these machines, because it's not the case that, you know, quantum computers plus Netflix equals quantum Netflix, which is better than regular Netflix. It's going to be about finding real opportunities to harness the core strengths of these devices. And that requires the intersection of two deep veins of knowledge. And that's why it's so hard.
Great. Okay, thank you very much. Well, thanks for the panelists. Thanks to SGInnovate for putting this all together. Thanks for the audience for listening. Thanks for the questions. And I'm certainly even more inspired than I was before. So I'll hand over back to Jin.
Thank you, Paul, and thank you to all our panel of speakers and for the great sharing, and thank you to everyone for your ongoing questions. It is always very heartening to see so much enthusiasm at our online sessions, but real conversations often happen after, so we do hope that all of you can keep connected. The recording of this session will also be uploaded on SGInnovate's YouTube channel, so do head on there for a review of today's event, and till our next online event. Bye, everyone.